matrix multiplications are something you learn in your first semester on linear algebra, or you have learned this in school. And it turns out matrix multiplications are super important in mathematics, but also in computer science and artificial intelligence. For example, we can use matrix multiplications for matrix inversion. We can compute the determinant from a matrix efficiently by using matrix multiplication. We can solve linear systems and so forth. But you can also use matrix multiplication for training neural networks, for example. You can use matrix multiplications for computer graphics and lots of other problems. So matrix multiplications are super important. And we will quickly draw something on the iPad, because you all should be familiar with how matrix multiplications work. And you have a matrix A and a matrix B, and in order to multiply them, there's a very nice visualization how to do this. So for example, we have our matrix A and our matrix B. So this is matrix A and this is B. And what we want to have is A times B. And say we have it's 2 by 2 matrices for now. So we have elements A11, A12, A21, and A22. And here we have elements B11, B12, B21, and B22. And we want to calculate our matrix. And for this first element here, in order to calculate it, we multiply A11 times B11, so something like this, and we add then the product of A12 and B21. Are you all familiar or proficient with matrix multiplications? Maybe thumbs up or thumbs down. Certainly something you should be fine with. And like this, you can calculate the other 4 entries anyway. But since you have learned this, we don't need to revise this. Now, we can think about the complexity of matrix multiplication. And concretely, we can say that A is a matrix that has M many rows, P many columns, and we can only multiply this with B if B has P, if B has P many rows, and then B can have N many columns. So this P must be the same. So P many columns in A and P many rows in B. So that dimension needs to be the same for both, that we can actually multiply them, and then M and N is something we can vary. If we want to know the complexity of matrix multiplication, then this is O of M times N times P, or we can just say that M times P times N and it's in the right order. So this is the O complexity, because I need to go through the M many rows, the P many columns, and from the other matrix, then the P many rows and the N many columns. So this is O of M times P times N. Now, if I say they are, say, all the same, or I just care for the largest dimension, then we just say the matrix multiplication is O of N to the third. This is the naive matrix multiplication, and obviously we can do this for matrices that are much larger than just 2 times 2 matrices. And now we are wondering if we are able to do matrix multiplication faster. Who of you, maybe without looking at the slides, does any one of you see an obvious way of how we can speed up matrix multiplication? If you see an obvious way, maybe thumbs up. If you don't see an obvious way, thumbs down. Just want to see if this looks trivial for anyone, if we can have something that is better than O of N to the third. So there is someone who sees something trivial. Maybe you want to share with us. So one student says, skip the rows or columns with only zeros. Yeah, maybe that could be a minor hack in some cases, but it doesn't necessarily improve the complexity. And we want something that actually improves the complexity. And in order to do this, we will quickly go back to the slides, because what I want to show to you is well formatted in the slides. And we will now look at the Strassen algorithm. It's an algorithm named after Volker Strassen. We will later see how it actually leads to an improved complexity of the matrix multiplication. And concretely, we have, for now, we only assume we have square matrices. And what's also important is the square matrices A and B. They must be of type 2 to the n times 2 to the n, so 2 to the n many rows and 2 to the n many columns. So A and B must have the same size. And if your matrices do not have this size, you need to make them bigger, and you just fill up the remaining spots with zeros. So that's important. But for now, we just assume they are of dimensions 2 to the n times 2 to the n. We only care about real numbers here. So we say A and B that we multiply, and then obviously C, which is the product of A and B, they are of dimensions 2 to the n times 2 to the n. We deal with real numbers. And we want to calculate this product, so of A times B. And we have just tried on one small example, so 2 times 2 matrices, how to calculate this product. And we will try to split these matrices into block matrices. So A and B could be relatively large matrices, and we will now split A and B each into 4 equally sized block matrices. So A11 is the upper left quarter, A12 is the upper right quarter, and so forth. So we split A, which is a very large matrix, into 4 equally sized blocks, and we do the same for B. That's why I'm also showing you this on the slides, because this is still bold. So we use a bold notation for a matrix A and in uppercase, and we have an A is still an uppercase and bold, so a capital bold. That means it's still a matrix, because before on my slides, I used a lowercase character, which was not bold, that was a scalar value, but here this is still a matrix. So A11 is a block matrix. And our result C that we want to calculate is eventually also now built or is also a block matrix of 4 equally sized blocks. And now we are wondering, what is this useful for? And it will take us a little bit to actually make it to the improved complexity. And we will write this out now on the iPad. So I will just write this down for you again, and then we will see what these block matrices are actually useful for. So here we say block matrices, and A, because on the iPad I'm hardly able to write A in bold. So this is just now in bold. That's why I've shown you this in the slides before. So A11, A12, A21, and A22. But remember, it's always in bold. And for our matrix B, we're doing the same. So B11, B12, B21, and B22. And our result C, that is the product of A and B, we also write C11, C12, C21, and C22. Remember, they're all in bold. And now I want to know, how can I actually, so these are all blocks. Sometimes you find for such block matrices also a notation that is sometimes splits this matrix into such blocks. This is something you would sometimes see in a different notation. And I want to know, how can I calculate this block C11? And it's exactly what I have done before. It's the same procedure, how I can calculate this block, but yet we will write it out once. So C11 will be a sum of two products. So it's A11 times B11 plus A12 times B21. And we could be doing this now for C12, C21, and C22 as well. You can very easily do this on your own if you wish. You will also see the solution in the slides. But something, and we will look at it in a moment that it's there, but what we see is we have one multiplication here, we have one here, we will have one here again. I'm just putting where we have the multiplications of the block matrices. So we will have, in sum, we will have still 8 multiplications. So, and we have these pluses, but the pluses don't matter for now. We only care about the multiplication. So switching to this block approach, that we have a very big matrix and we split it into blocks, and then we try to do this calculation with blocks. That means we still actually, we're not dealing with concrete numbers yet, but within these blocks, we again need to split them again into smaller blocks and smaller blocks recursively until we have scalar values that we can finally multiply and add. So what I've shown you here is just a top view. Actually, it's a recursive view. We need to dig deeper because this block here, so C11, is something you can again split into 4 equally sized blocks recursively. And that's why we said that A and B and C, we've said this before, A, B, and C, they need to be of dimensions 2 to the n times 2 to the n. And because this is the case, we can recursively split these blocks into smaller and smaller equally sized blocks until we deal with scalars. So far, this recursive approach to have a large matrix and split it into blocks rather than dealing with all the scalars directly doesn't lead to any improvement in terms of complexity. But it will very soon. And what I had just shown you was this calculation of C11, which is A11 times B11 plus A12 times B21. And these remaining 3 ones I had not written out, but I had shown you in total, it's still 8 multiplications. Now, we want to calculate this here using less multiplications. Do you think this is possible to calculate these 4 C's with less multiplications? If you think this is easily possible, thumbs up. If you don't see how to do this, maybe thumbs down. And no special cases like zeros or whatever, just in general. And it's probably none of us can see that easy because it isn't that easy. And it turns out you can calculate this here with less multiplications by introducing auxiliary variables. You can introduce 7 auxiliary matrices. I'm not deriving this for you. It took Mr. Strassen quite a while to derive this on his own decades ago. And what he derived are 7 helper matrices. And what I noticed, for each helper matrix, I only have 1 multiplication. I have a multiplication here, there, here, there, and so forth. I may have more additions or subtractions, but I have less multiplications for now. I only have 7 multiplications to create these auxiliary matrices. My goal was actually but to compute these C's, not these auxiliary ones, but for the auxiliary ones, I only have 7 multiplications. And then I can use additions and multiplications of these auxiliary ones to calculate my C11 to C22. So I introduce more multiplications and additions, but I have less multiplications. And multiplications are the expensive part of matrices, because if you add 2 matrices, adding 2 matrices is O of n squared, because I just need to go through both matrices at the same time. So it's O of n squared. I look at the first element of 2 matrices, then the next element, and I just add them together, or I subtract them, whatever. So multiplications are far more expensive than additions of matrices. And the Strassen algorithm re-expresses these 4 C's by adding and subtracting these auxiliary matrices and calculating the auxiliary matrices. I need to introduce additions, but I have less multiplications. I only have 7 multiplications, not 8. Feel free to try on your own if this is correct. You can obviously try to calculate this here on your own and test if C11 to C22 are correctly calculated. And you need these auxiliary matrices and finally add this here together. This is something I had sometimes put in some exams in the past as a sub-problem. So in some of the past problems, I had in some of the past exams, I had a big problem on the Strassen algorithm. And then maybe one tiny sub-problem was to show whether C11 is calculated correctly, and you need to show this. But you just plug in the auxiliary matrices and simplify the term, and eventually C11 has to look something like this. And if you try this, you will notice it's correct. So the Strassen algorithm works, and it's important. It does this recursively because just the block matrices alone are not enough, because you still need to break your block matrices into smaller block matrices until you have scalar values. So it's a recursive procedure. As before, when I had introduced this block notation, I also said it's recursive. But this time, using these auxiliary matrices, we can actually do this computation cheaper. And now you're wondering, what does cheaper mean? We are introducing more lower order terms, because additions and subtractions of matrices are lower order terms. So this adds more lower order terms, but we have less multiplications. And remember, it's a recursive procedure. And so this will definitely lead to far less multiplications in total. And now you're wondering, what's the impact? The impact is the Strassen algorithm has a complexity that is O of n to the binary logarithm of 7. So we have 7 multiplications, and we deal with the binary logarithm because we split a matrix into a 2 times 2 block matrix. So this is that binary logarithm. Had we split them in a different way, maybe a different logarithm, and then we have 7 multiplications rather than 8. And this actually leads to an improvement. If we use the regular naive matrix multiplication, say on these blocks we had first done without the auxiliary ones, then this would be n to the binary logarithm of 8, which is 3. So O of n to the third. And O of n to the 2.8074 approximately is a better complexity class. Do you feel this is a substantial improvement to n to the third or not? Maybe thumbs up if you think it's a substantial improvement, thumbs down if you don't think so. So maybe some more votes. There's a well, we are somehow evenly split, or now there's even a majority for it's not substantial. We will later see if it's substantial or not, but first of all, it's a better complexity. But it adds more lower order terms. Because of these larger lower order terms or large constant, this is something you would only do for matrices typically where you have more than 100 rows or columns. So for tiny matrices, you would not be running the Strassen algorithm. And if you look at like professional implementations of matrix or linear algebra libraries, then what you will often see is that they only use the Strassen algorithm or some other fast matrix multiplication algorithm if you have like more than 100 rows or columns, because then for larger n's, it actually starts to pay off. For very small n's, it actually takes longer. But we learned this about the O complexity. It's for large n's, so asymptotically. The Strassen algorithm comes with one drawback. The numerical stability is reduced. Numerical stability here comes into play if you deal like with real or like float values. With integers, it doesn't make a difference. But if you deal with float values, your result accuracy may be slightly diminished because you have more and more operations. And if you with float values, you have some loss of precision at a certain degree, and this could slightly diminish your result accuracy. But this is something also maybe not to be worried about in this course. Now, this is the Strassen algorithm. And now you're wondering, can we even do better than O of n to the 2.8? And is this actually substantial? Well, the Strassen algorithm is a substantial improvement over the naive matrix multiplications. If you make n very large, for example, in machine learning applications where you deal with huge matrices, then n to the 2.8 leads to a significant improvement compared to n to the third. Not really for super small matrices, but for very large ones, this is certainly something done. And this is something you would be doing if you professionally implement matrix multiplication, or if you use matrix multiplication, say, to train a neural net. The libraries in the background, they will use a fast matrix multiplication algorithm like the Strassen algorithm or some other fast matrix multiplication algorithm. And now we can wonder, are there better ones? Can we do better than 2.8? And in fact, over the years, more and more fast matrix multiplication algorithms have been proposed, and there are. So the naive matrix multiplication is O of n to the third, and then Strassen proposed his algorithm in the late 60s with 2.8 something. And this actually led to more and more papers improving matrix multiplication down to under 2.4, so 2.3 or 2.33, whatever. So there are improvements, but it turns out that essentially everything that came after Strassen is only purely theoretical. That these improvements, yes, they lead to a better N or to a better complexity, but only for super huge matrices that are too big to fit in nowadays computers. So something like this stuff down here, yes, it's better than Strassen, but we just don't have such large matrices that fit in our computer that this would actually lead to an improved running time. So for everything practical, the Strassen algorithm is actually the quasi best we can use. This is something I presented like this in this lecture until 2 years ago. 2 years ago, the lecture stopped here and we were done with the fast matrix multiplication. And then something happened about a year ago, or maybe a year and a half ago. And actually, a new matrix multiplication algorithm was found that is better than Strassen, not as good as the other ones, but better than Strassen, and is actually usable on nowadays matrices we are using. So the lower order terms added are not that substantial. So it actually can be used on matrices. And we'll talk about this now. So this is where the lecture ended 2 years ago. And last year it appeared, and I directly, or it maybe appeared a year and a half ago or something like this. And then I added it directly to this course. So you see, even a foundation course in algorithms and data structures is affected by advances in research. And what is super interesting is this paper that appeared. So it actually, yeah, it appeared in October 2022. So after I taught the course 2 years ago, but before I taught it 1 year ago. And this paper was published by DeepMind. DeepMind, who of you has heard about DeepMind? It's a company, maybe thumbs up, thumbs down if you ever heard about DeepMind. So some have heard. DeepMind is a subsidiary of Google, focused on artificial intelligence. They are the company that built AlphaGo, for example. So this AI that started to beat the best human Go players like 10 years ago or something like this, or 8 or 9 years ago. So that's that company. It's a subsidiary of Google. And they actually found a better fast matrix multiplication algorithm that works in practice. And they used an artificial intelligence in order to find that algorithm. So they did not manually like Strassen, because this probably took Strassen many, many days or years to come up with, to find this structure that was hidden in a matrix multiplication. But they found something, or DeepMind found a better matrix multiplication algorithm, but not by hand, but an AI actually found it. So they built an AI to do this. The AI is called AlphaTensor. What is a tensor, you may ask? So you know a vector goes along 1 dimension, a matrix goes along 2 dimensions, and a tensor goes among k many dimensions. So it's a generalization. So a vector or a matrix, they are tensors, but tensors can have more than just 2 dimensions. So you could have a matrix in 3D or in 10D, whatever. Tensors are also of use when you build complex neural networks, say complex convolutional neural networks or neural networks working on 3D data. Typically, you would be using some tensor approach. So this is what a tensor means. And the AI proposed by DeepMind is called AlphaTensor, and it's an AI that finds fast matrix multiplication algorithms. It actually builds on AlphaZero, and AlphaZero is one of the AIs that achieved superhuman performance in playing the board game of Go. The first DeepMind AI that bet the best human players on Go was called AlphaGo, and AlphaZero was the next one, an extension or an improved version. And that AI that was used to play the game of Go or learn this, it actually turned out it can be reused for many other things, or this approach. It can be used to improve a Google search, but it can also be used for AlphaTensor. We don't discuss in this algorithms and data structures course how AlphaZero works, because for this you need quite a lot of AI background, which is not the idea of this course. But we will see what AlphaZero actually delivered. And AlphaZero found multiple fast matrix multiplication algorithms. One of them worked particularly well by multiplying 4 times 4 matrices. So actually matrices that are not size 2 times 2, but 4 times 4, so a different size. And in order to do this, say in a naive way, you would need 49 scalar multiplications. So before we've seen that 2 times 2 matrices, we would need 8 scalar multiplications, was reduced. And now with these 4 times 4 matrices, in a naive way, we would need 49 scalar multiplications. But with this algorithm found by AlphaTensor, we only need 47 of those. And what you see down here is a comparison of such algorithms. So multiplying a 2 times 2 with a 2 times 2 matrix, so Mn and P, this was used using the Strassen algorithm. And I'm sorry, the 49 here is obviously not the naive one, but it's actually the Strassen algorithm. The Strassen algorithm applied not to 2 times 2, but 4 times 4 matrices. And this is exactly shown here. So Strassen, the Strassen algorithm from the first period could also be used for 4 times 4 matrices. And you would have 49 multiplications with the Strassen algorithm. The naive one would obviously be more than 49. And this new algorithm proposed by DeepMind, or which was found by AlphaTensor, for such 4 times 4 matrices only needs 47 multiplications, not 49. And for the 2 times 2 matrices, it didn't find anything better. It found a Strassen algorithm again, and I think some equivalent ones, but it didn't lead to an improvement. But for larger matrices, so splitting this huge matrix not in 2 times 2, but 4 times 4 ones, we would actually be able to do this with less multiplications. And this is 47 multiplications rather than 49. And does that lead to an improved complexity? Yes. Before I said for the Strassen algorithm, we had a log 2, so a binary log of 7, because we had needed 7 multiplications, and we used 2 times 2 matrices. Now we use 4 times 4 matrices, so we need log 4 of 47 multiplications. And this leads to a slightly improved complexity, because the complexity is O of n to the 2.77. And if we use the Strassen algorithm, say not for 2 times 2 matrices, but 4 times 4, so one more step in the recursion, this would be log 4 of 49, which is just the complexity from before, so the 2.8. And now we got even better. And what we got better is just tiny, but still for large n's, it runs faster. And this actually is usable in practice, which makes a huge difference compared to all these other fast matrix multiplication algorithms that were derived over the years, because they have a better complexity, but not for the data we have available. So this is something super interesting, and you can now see how even artificial intelligence impacts your introductory course to algorithms and data structures, because an AI has now allowed us to find a better matrix multiplication algorithm. We look at what the algorithm looks like in a moment. And I think this is something we're going to see more and more in the coming years, in computer science, because we have a lot of heuristics and a lot of foundation algorithms that super smart people came up with 50 or 60 years ago, and others were not able to improve these heuristics further. But now with an AI, we can probably improve these heuristics. And I think this is something we're going to see more and more in the coming years, with foundation algorithms that are being replaced by new foundation algorithms that were not found by humans, but by an AI. So it's a super exciting time. And many professors think that once they have created their slides for algorithms and data structures, they would never have to change them again for the rest of their career. I don't think so, because we will see more and more of this. And maybe in the future, we will see, I don't know, improved sorting algorithms. Something like this was even proposed by DeepMind, improved sorting algorithms, not for large data sets, but for super small data sets, like I think sorting 2 or 3 numbers or something. DeepMind built an AI that found an algorithm that needs less steps in assembly code in order to sort something. So stuff like this, we're going to see more and more. That one, the other one I just mentioned, did not improve the complexity, but the effective runtime. And so we're going to see more and more of this, I think, in the coming years. Now, what does the new algorithm look like? So we have 4 times 4 matrices, and we have this result here, C, which is the product of A and B. And it actually turns out that you can calculate C11 up to C44, but you need a lot of auxiliary matrices. The auxiliary matrices, they come with less multiplications. Yes, they come with 47 multiplications, not with 49, but it's certainly far more difficult to look into this than the Strassen algorithm. So you don't need to remember this by heart or to prove that it's correct. This was done by others. We don't need to do this, but we see we have far more auxiliary matrices, and it's far more complex to calculate the final blocks, but it leads to an improvement. So this is how AI is impacting matrix multiplication. And there are also some theories about how to use quantum computers for fast matrix multiplication. But this is something we won't be discussing for now, because quantum computing is something we'll discuss in the next lecture. There's a question here, why are 1,000 additions better than a few multiplications? Because I've always said we deal with blocks. We have large matrices that we split into smaller and smaller blocks. And when you add 2 matrices, so 2 blocks, then this is O of n squared, while multiplying would be O of n to the third. So we talk about large data sets, but this new algorithm proposed by DeepMind, maybe you wouldn't be using it for 100 times 100 times matrices, but maybe for 100,000 times 100,000 or some other threshold. You would need to see the paper, what a suitable threshold would be. But this is now some data you're going to deal with when you train large neural networks. And then you rather have more additions of blocks than multiplying blocks.